Hello everyone, my name is Filip and I work at marketing here in Codasip. And today we will talk about PPA, which stands for performance, power, and area. And these are the basic metrics that many SoC designers are interested in when searching for the right processor IP solution. Especially the performance is very typically crucial. And this is why I'm happy to welcome Pavel Schnobel, the team leader of a compiler group here in Codasip, to discuss how compiler is influencing processor performance.
Hi, Philip. Thank you for having me. This topic is something we get questioned about all the time.
That's great. Actually, I want to remind everyone that Roddy has covered this topic in a previous installment of this video blog. So you can watch that and learn how the various benchmarks available on the market can help you to measure the processor performance. But for the viewers we have today, Pavel, can we briefly explain how benchmarks are used?
Sure, Philip. So benchmarks are basically synthetic programs specially designed to measure performance. And by synthetic programs, I mean that these are not like real applications. These are really programs written specifically for the purpose of measuring performance. So what you typically do is that you take the benchmark, you compile it, and you run it on your processor. And at the end, you get a number. And the number is called a score, and it tells you the performance of your core on this benchmark.
Okay, thank you. That was a good explanation. And actually, what is happening is that these designers are typically looking for the right balance between the performance they need and the power consumption and area which will come with such performance. And if they need to go to a higher performance, they also should assume that the power consumption and area will grow. However, what is important to discuss today is how is compiler influencing this performance?
Okay, well, the compiler is the tool that basically takes the code of the benchmark and produces the instructions that are run on the processor when executing the benchmark. So the compiler affects how many and what instructions the processor actually runs when executing the benchmark. So if the compiler produces code that leads like to fewer instructions executed, then you typically get a higher score on the benchmark.
Okay, good. So it can almost sound like the compiler is this magic tool which will bring a lot of performance to your processor, but will not sacrifice any power consumption or area. Is that correct, Pavel?
Well, unfortunately, it's not that simple. Most optimizations used in modern compilers that increase performance, they also increase code size. So when the optimization, when the performance goes up, then so does code size, unfortunately. Yes, so that's the idea.
So is there any way to show this in a simple example?
Sure, I'll show it using a couple of slides. So on this slide, you can see a simple example of a program, or it's more like a snippet of code that basically executes what's called a multiply and accumulate operation in a loop. So multiply and accumulate is basically that you take two values, you multiply them, and you add them to an accumulator. And in this loop, the operation is executed 4 times. And what is important to realize here is that in each iteration of the loop, you're not only executing the multiply and accumulate operation, you're also executing what's called a loop overhead. So it's instructions related to the loop, instructions needed in order for the loop to work. So in this case, in each iteration, you have to increment the variable I. You have to check it against the bounds of the loop. So you have to check it against the end value. And if the condition is true and I is less than 4, then you have to jump back at the start of the loop to start the new iteration. So what the compiler can do to reduce this overhead related to loops is that it can unroll the loop. So it can, for example, unroll the loop twice, as shown on this example. And now the loop overhead is executed only once per 2 iterations of the original loop. So you do 2 multiply and accumulate operations, and then you execute the loop overhead instructions. So the loop overhead effectively is now only half of what it was. So performance goes up. But at the same time, in order to do this, you had to, or the compiler had to replicate the loop body. So code size possibly increased. So as I mentioned previously, performance goes up, but so does code size. And what the compiler can also do, as shown on this example, it can fully unroll the loop. So it can remove the original loop altogether, and now there is no loop overhead. So performance goes up again. But in order to do this, the compiler had to replicate the loop body 4 times in this case. So code size increased even more. And what I would like to say here is that the fact that increasing performance leads to increasing code size, it may or may not be a problem depending on your use case. On some programs, it may not be a problem. In some cases, it could be. But I think that this is really something that you should be aware of, that when one metric goes up, then so does some other metric. And typically, one statement in the original C program corresponds to several instructions of the instruction set. So this depends on the architecture, but it is usually so. So the code size may increase even more than it seems from the original C program. And on this slide, you can see basically a summary of what I just mentioned. So when you fully unroll the loop, you now, instead of one multiply and accumulate, instead of one multiply and add operations, you now get basically four multiplications and 4 additions.
So, Pavel, thank you for this explanation. I believe that was very clear, and it's exactly the simple example that I was looking for to explain this to the vast audience that we hopefully had. But how does this influence benchmarking, if it does?
Well, optimizations like the one I just showed, loop unrolling, are used on benchmarks all the time. And this problem I was trying to explain, it's not related only to loop unrolling, it's a general problem. So for instance, another typical optimization is function inlining, where you basically take a body of a function and put it where the original call to the function was. So you remove the overhead related to calling a function and returning from a function, but you effectively have to duplicate the entire body of the function. Optimizations like this, they are normally used in all the benchmarks. So what's important to realize here is that the score on typical benchmarks like Cormark or Drystone is not based on code size. It doesn't take code size into account at all. It's based only on performance. So when you compile benchmarks, you typically use the compilation flags that lead to the best possible performance, and you don't care about the code size implications these options might have. But I suppose that things like this isn't a problem just when measuring performance, right? This is similar when measuring things like power consumption or area, right, Philip?
Yes, you're absolutely correct, Pavel. When measuring the power consumption and area, what very often happens is that when presenting such numbers, these are relevant for one of the possible configurations of the processor. And typically, this is one of the simple configurations. However, it doesn't mean that all the people who will then integrate such processor in their SoC will choose this minimal configuration. So then the actual area and power consumption would be also bigger. What is happening here is we are mentioning a lot of negative aspects of measuring PPA. But I still believe that, for example, the benchmarking is a relevant way that many people will use, at least for the very first comparisons between different solutions in the processor IP market. So can we give them some advice which can actually help them to do this well?
Well, I mean, when you'll be using your processor, you won't be using it to run benchmarks, right? You'll be using it to run your actual application or applications. So I think that the best advice is not to rely on benchmarks and actually try how your application performs on the various cores you're considering. But at the same time, I understand that this isn't always possible. And sometimes you cannot just take your application and run it on all the possible cores. And in such case, you have to rely on the benchmark numbers reported by the vendors. So in such case, my advice would be that you should make sure that you're actually comparing apples to apples. So you should make sure that the benchmarks were compiled with the same compiler and using the same compilation flags, because otherwise the differences in the scores may not be caused by actual differences in performance of the cores. They may be just caused by the fact that the benchmarks were compiled in each case.
Yeah, what you say is exactly what we try to encourage our customers to do, to always request a evaluation license, which brings you the processor IP with the SDK that allows you to test the processor performance on the application that you actually plan to run on it. However, I do understand that there is a temptation to go for solutions which present a very minimal area, but still a very significant performance on the same processor.
Yeah, I think that if performance or area is really important to you, then you will always pay the price in the other metric if you choose to go with a general purpose solution.
Yeah, and that's actually something we need to mention that Codasip can help you with, because we offer Codasip Studio, which is a tool which can move you from the general purpose processor domain into application specific processor domain. And these processors are optimized for the very application that you will run on the processor. So the PPA that you will have then are much better than if you choose to go with a general purpose processor. However, this is something that you can learn more on our website. You can ask any of us to give you advice on where to search information or to talk to us. So thank you again, Pavel. It was really great to see how you could demonstrate these typically very complex things that we try to explain to our potential customers in these quite simple examples, which still cover the root cause of it.
Yes, Filip, thank you for having me again.
And to all of our viewers, please visit our website. You will find all the products that we have discussed with Pavel here today described in more detail there. Feel free to contact any of us for more information and also visit some of our previous blog posts. Thank you.